Okay, so in this video, I want to talk about the following idea that it's kind of the case that if you know how to, like, if you were a god that could solve literally any first order system that came across uh, that came to your attention, you could solve really any ordinary differential equation or system of ordinary differential equations. First order systems are really all you need, even to tackle higher order differential equations or systems of them. Really, first order systems are all you need. And I want to demonstrate this just really quickly. Um, so, yeah, first order systems are all you need. So, for example, let's say that you had a very high order ordinary differential equation. Like, let's say that you had an order n differential equation. Like, you had something like the nth derivative of y is equal to some crazy function of, well, the independent variable, let's call that x, but also all of the derivatives up to the n minus first derivative. So maybe you had y of n minus 1, sorry, not of n minus 1, but rather the n minus first derivative of y, the n minus second derivative of y. You had all the derivatives in here as bits, as input to this function f. This is basically saying you have this big, crazy expression involving all of these terms. You have the first derivative of y, maybe, and then you have y itself. So this is some crazy, crazy order n differential equation. My claim is that this can be converted into a system of first order equations. Can be converted into a system of first order equations, which, if solved, would give you a solution to the differential equation in blue here. Let me call this equation here star. Okay, would solve star. You understand what I'm saying? Okay, so what is that system? So what we're going to do is introduce a bunch of variables. We'll call these variables u1 through un. u1 through un. Okay, so the n dependent variables are all going to depend on x in some way. And here is, I'm going to write down now for you a system of first order equations. Here's the first equation. We're going to take u1 prime to be equal to u2. You agree with me? That's a first order equation. We're going to take u2 prime. Why first order? Because it only involves a first derivative. Here's another equation. u2 prime will be u3. Suspicious. u3 prime is going to be u4, and we continue in this way. So I'll put a dot, dot, dot here until we get to u sub n minus 1. The derivative of that is going to be u sub n. Okay. So far we have n minus 1 equations. I'm going to add one more. This last equation is going to be u sub n prime is equal to this same function f, this function here. But now, instead of putting in x and all the derivatives of y, I'm going to put in x and then all of these variables that I've got here, like un minus 1, all the way down to u1. And my claim, and I want you to think about this, is that if you solve this system in red, and this is a system of first order equations. Whoa, sorry. This is a system. I was moving a hair that was on my iPad. This is a system of first order equations. If you solve this system, then you've solved this blue equation up here. Why? Because U1, whatever U1 is, whatever U1 ends up being in your solution, that's the solution to your differential equation. Why? Okay, so let's think about it. So U1, if solved, then U1 solves star. In other words, U1 and all of its derivatives, when plugged into this f, is going to give you the nth derivative of U1. Okay, so why? Why is that? Well, because what is the first equation saying? The first equation is essentially saying that U2 is U1 prime. U2 is U1 prime. But then, so yeah, this equation is sort of saying, I mean, I feel stupid even writing this because I'm just writing what this thing says. But U1 prime is equal to U2. No kidding, right? What does though this equation kind of say? Well, if U2 is U1 prime, if U2 is U1 prime, and U2 prime is U3, then isn't it the case that U1 double prime, just take the derivative of this equation, both sides. You get that U1 double prime is U2 prime, but U2 prime is U3. So in other words, this tells us that U1 double prime, that's U3. And then this is telling us that U1 triple prime, similarly, is U4. And you get it all the way up to up here, U1, I believe, n minus first derivative of U1. This is exactly U sub n minus 1. No, this is U sub n on the nose. Sorry, my bad. Yeah. And then this last equation is telling us that un prime is exactly equal to f of all this other stuff, of all the derivatives of u1. But that's exactly what this equation here is asserting. Okay? I hope that this makes sense, okay? Now, with this idea, you can take any higher order differential equation and convert it into a system of first order equations. Okay, so this is powerful. And the reason why this is useful is because you know what really likes solving first order equations numerically? Computers love solving first order equations numerically. And there are numerical issues around trying to that make it so that computers even prefer solving first order systems relative to like trying to solve a second order equation. Like it would rather attack a system of first order equations rather than a single second order equation, right? I'm not describing what those issues are, just that they exist. So you might find it useful in your life if you have a complicated differential equation that you need to solve numerically using a computer to first convert that into a system of differential equations. Similarly, if you have a system of second order equations, you can convert each of those second order equations into first order equations. So not only can you attack and kill higher order differential equations like this one, but you can attack and kill higher order systems just by converting each of the individual equations into their counterparts in the first order realm. Okay, this is the idea. All right, and once you do that, you understand all you need are first order equations. Okay. Okay, one more video I want to do. This time is just about visualizing and maybe a few comments about existence and uniqueness of solutions. Okay, see you in the last one.